So now I will start. Welcome to everybody. We are a lot of people here in the room, and there are some people, Jaione and Maria Jose, and many other people are in the chat. So welcome to this course, but also to the seminar of this month that is within also the framework of chemometrically speaking. Jens, chemometrically speaking, is just a bunch of people that we gather together for every month, once every month, and we bring a topic that is focused in chemometrics, but also in more technical chemometrics, but some more in applied things. And for instance, for you to understand better, we had Federico Marini giving ASCA. That was very technical. But we also had Ludovic Duponchel talking about LIPS, laser-induced breakdown spectroscopy, and chemometrics.
Okay.
So I thought that joining the seminar and also this group, this chemometrically speaking, it was excellent idea to invite you. Okay, so I will introduce you just a little bit. Jens Peter Ball, you work at NOFIMA. NOFIMA is a very important food institute there in Norway, and you are based in Ås, right?
Yes, we are based in Ås. That's 30 kilometers south of Oslo.
And you have you have a strong expertise in optics, in spectroscopy, in hyperspectral imaging, and especially how you implement these hyperspectral devices into real scenarios, real industrial scenarios. So I think that you are the perfect one to talk to teach us a little bit how we implement hyperspectral cameras in industries. So Jens, with no more ado, the public is yours. If you want to add something else in your presentation, that would be fine. But otherwise, you just
Great, thank you, Jose. It's very nice to be invited. Of course, I think the topics that you are working on these days in your workshop is well. I hope that my presentation will be relevant. I will I will not go much detailed on much of this, but I will tell some stories and tell about some applications that I have been working on over the years, and I hope it can be of interest for you. I will. So I work in the Food Research Institute, and many of the applications that I will show are typical Norwegian things, Norwegian foods. If you are in the Basque country, you will probably like a nice example from bacalao that I will show that started everything.
Jens, you are mute.
Sorry. Okay.
Yeah. After saying bacalao, that was the last we heard.
Yeah. Okay. I will show you some examples from bacalao. But just some words, a couple of more words about who I am, my background. I have a master's in signal processing, and I have a PhD in spectroscopic methods for food quality measurements. I have many years of experience with visible spectroscopy and NIR, Raman, fluorescence, and spectral imaging. And I've been working in the area for quite some years now, and I have always been working quite closely with the food industry and also instrument developers, either companies or other researchers in the that are doing optical instrument development. And that means that I really enjoy multidisciplinary work and collaboration. And if I didn't do this collaboration, we wouldn't get that far. I wouldn't be able to do the things that I show you alone. So it's very important that we all work together to, in a way, make, for instance, hyperspectral imaging possible. I would say I'm more a problem solver than an academic. That I'm motivated by solving problems, but I also like to publish problems that we have solved. So much of what I will show you here, you can read about in papers if you are interested. So right now and the last years, I've been ahead of a long-term research program. It's called DigiFoods, where the main aim is to develop inline sensor systems that works well in industrial lines. So it's very similar maybe to what you are talking about today. So the motivation behind all this work is that, as you know, there is an enormous variation in raw material quality in throughout the food industry, and even if these products they look quite similar, they are very different, and they should be treated differently. So you have different amounts of, for instance, dry matter in potatoes, different amount of fat in salmon, and a different amount of food in crabs. And if you in a way treat every crab the same, then the company will just lose a lot of money and deliver poor quality and so on. So it means that we have to utilize this variation in the best possible way, both for sustainability and for increased profitability. And our mantra here at NOFIMA is that if you can't measure, you can't control. So you need to be able to do proper measurements in the process lines to be able to, for instance, sort or adjust your process in a best possible way. And it's quite can often be difficult with foods because they are so extremely heterogeneous and difficult from a measurement point of view. But here are some examples of solutions that I will show you and talk about. Up here in the corner is chicken fillets. So this is spectral imaging. Sorry, in true time. Here is spectral imaging of salmon and also of the crabs. And I also work with many other methods. So the potato here is point measurement, also experiments in the industry. So as I said, we try to solve different problems out in the industry, and then sometimes hyperspectral imaging is needed, but often of course it's not needed. Then we can use point measurements or not NIR, maybe Raman or maybe fluorescence. It all depends on the problem. But all the time I've been working with foods, my main, in a way, interest and main concern when I work on spectroscopy has often been about sampling, representative sampling, because as I said, all these difficult samples, and foods, if when you want to measure, for instance, fat content in a salmon fillet, then it's quite, or it can be challenging because the fat is not evenly distributed. There's much more fat, for instance, in the belly than in the loin, and there's much more fat in the front of the fillet than it is in the tail. So everything is just unevenly distributed. And if you want to measure on a whole salmon, which we have done and can do, then you have to measure through the skin. So you have to measure in depth. If we want to measure with meat or do measurements on meat and beef as here, then you have to also handle the heterogeneity. So much of my talk will be actually about representative sampling, and that is the main reason why I have been using imaging, spectral imaging, because it's an excellent tool to really get a good optical or spectroscopic sampling of your samples. I wanted to just start with a story that started around in 2005, actually. So a long time ago, where we had a project where the main aim was to measure the water content in dried salted cod. Like in Norway, we call it bacalao. That's for you in Spain, it's bacalao is for cod in general, but this is dried salted cod or clipfish. And I know that in the Basque area in Spain, it's very popular, and I really love this kind of food. But it's very challenging to measure the food, no, the water content. So the water content is important. So the higher the content is, the lower the price. And also the drier the fish is, the higher price, and you can store it longer and so on. And it also affects the texture and let's say eating quality. But the most important thing for the Norwegian industry, because most of this fish is produced in Norway, is that they need to know the water content, because the water content actually decides the price. And this product is complicated for instance, NIR, because it is the water is unevenly distributed, so there's a lot of water in the middle thick part of the fish. It is much drier out on the belly flaps, and it's also drier towards the tail. And it's dry on the surface, also covered with salt sometimes, but it's more humid, more water inside. So all of this makes it quite difficult, and I wanted to try NIR, and people around me said, well, just drop it, because don't waste your time, because this is too complicated. But then we wanted to check, okay, what kind of NIR measurement can we use to actually get proper measurements? So first we wanted to check, is it possible to get good water measurements with reflection measurements, where you just use ordinary NIR in reflection mode, measure the reflected light from the surface? Or do we have to use what's called interaction, which is normally that you use optical fibers, you send in the NIR light, and the light you measured has been to some depth in the fish. And to make this feasible in the industry, we had to do it without any contact. So my partners in optics, they made this special probe that we could measure interaction in non-contact. And so what we did, a simple experiment where we took out from 20 fish, we took out a square, the blue square here, and we measured it with NIR with these three methods at different areas, as you see there. And then we homogenized those square samples and measured them again, just to compare how were the results. And here are results for the homogenized samples. I mean, and that's easy. And then you can see that all the methods, reflectance and interactance, they gave about the same accuracy. So to the right here, you see the root mean square error of cross-validation, prediction error, should be as low as possible, and it was about 0.6% points. But when we looked how it worked on the intact samples, then you can see that reflectance had a quite high prediction error, almost 2%, but the two other methods had much lower prediction error, around 1.2. And so it just told us that, okay, to be able to do proper measurements on this kind of fish, we need to measure in depth. So that was the first stage in this research project, and this case is the same for a lot of food products. You need to measure in some depth to actually get good and representative samples. You don't have to if the surface is representative for what you want to measure, but in foods, that's often not the case. And then the next step was, okay, we need to measure in some depth, but how much of the sample do we actually have to need? So the reference sample for this product is that they cut out these slices, cross sections from the fish, and then they cut them in pieces and they weigh them and dry them and weigh them, and then they get the water content. So it's extremely cumbersome. It takes a lot of time. So what we wanted to do was, is it enough to measure, for instance, just this red spot here, or is it better if you measure a line, or is it okay to measure a square here, or do we actually have to measure the whole fish with NIR? And then we got the results for that as well. So you can see here, if you measure the point, then here we have a calibration based on 50 fish where we did this. So if you measure a point, you got a prediction error of 1.4, which was not good. If we increase to a line, then we got 1.2, which was okay, a bit better, but not as good as we wanted. But if you measure the whole square or the whole fish, or actually if you measure along all the lines that I show you, you can get a much better model and a low prediction error. So that means that okay, we need to actually measure most of the fish and in depth to get a good good measurements. You can't fix poor measurements with chemometrics. I mean, you know that. So, I mean, if you have garbage in, you will have garbage out. So it's extremely important to work on your measurement situation to obtain the most representative measurements with regard to what you actually want to measure. So that ended up in this actually novel system at that time. So I worked with a technical institute called SINTEF in Oslo. They are experts in optical instrumentation. They had already made hyperspectral imaging for inline sorting of plastic materials, and they at that time we took that system and we adjusted it so that we could measure in NIR region with deep penetration possibilities, the same range as I understand you are working in. So it's about 850 to 1050 nanometers, which has a good penetration depth. And this system is actually a scanning system. So this is a new version. So what it does, I can just show this video here. This is scanning of a fish, and then you get what you see out to the right here. You get a hyperspectral image. In this case, it has 15 wavelengths in the visible and 15 in the NIR. And you would think, oh, that's very few wavelengths, but you don't need more wavelengths in this region. The features are so overlapping anyway. So with 15 wavelengths in the NIR region, we can measure almost everything that is of interest in that region. You can also see that the spatial resolution here is also very low. But I mean, for these big samples and for a lot of other food samples, it doesn't matter. So the pixels are big and the resolution, spectral resolution, is low, and the reason for that is to optimize the signal to noise so that we get as much light as possible when we do the measurements, and especially since this is not reflection, since we are measuring in the depth in the sample, then the signals we get back are even weaker than what we would get in if we measured in reflection. And this is a flying beam system, so it's actually not a camera. It's a flying beam where you are illuminating two spots, one on each side here, and you have a system that measures the light coming up between. So that means that you are measuring in depth here, maybe in this fish, maybe 1 centimeter, which is enough. And then this beam is scanning very quickly across the belt here, collecting thousands of samples per second, and can build this up to an image. So it's a rather conventional system, probably to what you are used to. It's not an ordinary camera. Yes.
Yes. One question here. You don't have the problem of kind of burning the sample or damaging the sample when you are scanning it with that amount of light?
You don't have to damage the sample, no. It's completely non-destructive, if that was what you mean. Or did I understand?
But I mean, as you have to give a high amount of light, maybe you generate some heat, and that could.
Yes. No, it's not. It's not damaging at all. So I mean, it's not that warm. It's no problem for me to hold my hand under the beam here. So you won't notice much heat there. Then you have to keep it there for a long time. So it's no problem, and especially not for foods. I mean, foods contain maybe 70% water or something. So it's no problem. Yeah. So what you get out then? Okay, was that answer? Okay. Yeah. So
it was just thanks.
Yeah. So this is what we get out of this system. It's spectra from in this region from about 760 to 1040. You have the water peak here at around 980. You can't see it here, but you have fat at around 930. You have protein around 1020, and so on. And based on in this case, these are just average spectra from some fish, and then based on that, we could make really quite nice calibration models for water in the fish, and that again, those models could worked also quite well at pixel level. So in this industry, they went from a very old-fashioned, let's say, manual classification of each fish, because what they did and still do some places is that they bend each fish to estimate the water content. But now they could measure every fish, and they could see how the water was distributed and so on, and they used it in some drying projects. And it was implemented in 2007 with this the first version of this machine, and here you can see how it looks out in the industry. It's quite old-fashioned. It still is. But where they can actually measure water content in the fish, and it was used quite a lot. It's not used that much now, but now they are very eager to start again, because the rules, for instance, in Brazil and Portugal now for import of bacalhau is much stricter. So they are checking the fish when it arrives, and they measure the water content. So this was in a way the first thing I did on industrial imaging. And the examples I will show in the next examples is based much on this system. And I will go more into some different calibration strategies that we have looked into for this kind of images. So as I said, here at the left is the first version of the system, and that then it was not the flying beam. It was stationary illumination across the belt, and but the sensor was scanning across the belt. So but stationary illumination. So I like this system quite well, but it had some disadvantages, because we had a shield here to separate the incoming light from the light that we measured, because this is still measuring in interactance. So here is the newer version that was developed maybe in 2008 or something. And this is this flying beam. It is made by Tomra Sorting Solution. And it's used now worldwide, especially in the meat industry. So if you can buy this system, it costs maybe I don't know what the cost is now, maybe 140,000 euro or something. It's not cheap, but it's completely made for industrial measurements.
Jens, you are mute again. Not only mute, he disappeared. Igual se pone a hablar. Oh.
Sorry about that.
Hello. Yes. Yeah,
Hi.
we missed you.
I'm back. Sorry. I
We
will-
were just wondering, how long did you take to realize that you were out?
yeah, I don't know. How long did you wait?
No, just 30 seconds or
Okay,
You were about to start the next sample.
yes, you changed the slide and
maybe I
Previous
was.
one.
Maybe I
okay.
was
Yeah, you were in the
There.
slide. Yeah,
here.
that one.
Okay. Yes, as I said, we are producing a lot of salmon in Norway, and it's important for the industry and also for those who are breeding salmon to know as much as possible about the chemical composition. That means mainly fat content, but also pigment is of interest in the salmon. So we used the same scanner, and we wanted to calibrate it to measure fat content in the fillets. And here you can see in the NIR region, you have these 15 channels from 760 to 1040. So alone, they are not very interesting, of course, but we have a lot of then information in each pixel. So we wanted to do chemical imaging. They are interested in the average fat, but they also are interested in how the fat is distributed, because it's important in many ways for portioning and for trimming and also for genetics actually and breeding. So we figured out after a while the best way to do this. So I would say in general, when you want to make calibrations for a product, you always have to consider quite carefully, well, how do you do this in the best possible way? You have to understand quite well how, in this case, how is the fat actually distributed. So it's very important to know your sample. So in this case, we know that as I said, there's a lot of fat in the belly. There's less fat in the loin, not so much fat in the tail, more fat in the neck. We also know that there's actually quite little fat on the surface of the fillet. So the closer you get to the skin, the more fat there is. So in this case, it was also important to measure in depth, because I know that if you try to measure fat content just on the surface, you don't get that good results with fat. So what we did to get from a fillet to this chemical image is.
Yeah, Jens, you are mute again.
This is I have this thing on my cord that is sorry. Okay, this is something you probably done you too. I'm just showing it because this is how we did it at the time. So what we did was that the fat variation around on the fillet is much bigger than between fillets. So we took out samples from the fillet and we took these small plugs because we could put them directly into an NMR, low field NMR machine, and measure fat content. So that means that from every point on a fillet, we took out all these fat values, and we did it on a lot of fillets. And then from the hyperspectral image, we just match them with spectra from the same region, like this. So then we have our calibration set, we have our spectra, and we have our reference values, many more than what I show here. And I would say later we have done, to make better calibrations, we use bigger areas, but it was very convenient for us to take these small areas because we had this NMR machine to do the easy. I mean, it was quicker to do. But anyway, this is an okay for wave to do the salmon. And then based on that, we get a regression vector, which highlights the fat peak, and the water is in a way down weighted. So it's a very simple model, maybe 2 or 3 components. And then we can use that regression coefficient in every pixel in the new images. So here you can see how the fat is distributed. A lot of fat in the belly and so on, and we can also estimate the average the average fat content for this fish. And this is used today in the Norwegian fish industry to sort fillets, and it's very rapid. It's also used a lot by breeding companies to, in a way, evaluate their families. So there's maybe 4 times a week, 4 times a year, they slaughter maybe 5,000 fish, and then they measure every fillet, and they are characterized by this system. Okay, yx and the regression vector. So this is a little bit of geometrics. Okay. Another example I wanted to show you, mainly because it's not regression, it is ice fraction in super chilled salmon. It's a very special example, but anyway, it's nice to show. So a way to chill salmon is that it is super chilled. So you freeze it for at a very low temperature for a short while, and then you get a layer of ice, and that ice will spread out in the whole fillet. And it will be what we call super chilled. That means that a fraction of the ice is a fraction of the water is ice, maybe 10% or 15%, and then we can transport it to Europe much cheaper because we don't have to use all the ice on the fish. So we can save a lot of volume, and the quality is actually quite good. But the reference method to measure the ice fraction here is extremely destructive, and it quite difficult to do. And the guys who, in a way, tune this method, this freezing method, they really needed to be able to measure the ice fraction much more efficiently. And they also would like to see the distribution of the ice fraction. So then we again use this system because in NIR, when water turns into ice, we have these huge changes. So here, this black line here is from unfrozen salmon, where we have the water peak here around 980. And then when more and more of the water is frozen, then the whole peak shifts. It's a parent shift to higher wavelengths. So this dotted line here is from a deep frozen fish, and that means that it was quite easy to actually measure and quantify the amount of ice fraction. And in this case, we tried with regression, but it wasn't that easy because the regression, the fat and water, in a way, when you have this big shift in water, then it wasn't that easy to make good calibration because the fat, in a way, interfered. So what we did in that case, which is not that common in NIR spectroscopy, but we used curve resolution, MCR, where you can actually decompose the spectra here into 3 components. You have one fat component, you have one water component for liquid water, and you have one ice component that indicates the amount of ice. And then we could actually make images of the ice fraction. This one isn't very interesting, but we could see the the fat content, and we can see the total water. And we could then look at the pixel, or we could look at the ice fraction in every pixel. So if it did it by PLS, it didn't work optimal, as I said, because it was difficult to make a calibration in this case that could handle the variation both in fat and water. But if we used curve resolution, then we could calculate the ice fraction as the scores from ice divided by the scores of ice and the scores of water. I mean, it gave a quite good impression of the concentration of ice fraction. So then this is the same fillet, and you can see that the ice fraction is the picture is quite different, and this picture was more correct than the one we got with the PLS regression. So that means that this shows a picture of a salmon that is towing, and where we can actually make images of the ice fraction. And it's not used in the industry today, but it was used by this team who developed the method and figured out the optimal settings for super chilling. So it made their work much more efficient. So, and it's actually became the front page of this Journal of Spectral Imaging. I don't know if you are familiar with it, but I just think it was a bit funny. So that was another salmon case. So let's turn on to meat and beef. So here are spectra from beef of varying fat content. So there will be a lot of fat content now also, but there will be some other things later. This is in the same spectral region, which I think is of interest to you. You have this strong fat peak here at around 930, and the water peak around 980. And here are typical. We worked again with Tomra, this company who made this machine. So now it worked for this dried fish, it worked for salmon, but they saw that the big market, the really big market worldwide, is meat. And there was a big need in the meat industry to be able to measure fat content in ground meat, but also meat trimmings on conveyor belts. And it's not very easy, but I will show you how this is actually useful, and it is used worldwide today. So meat trimmings are, as you see, extremely heterogeneous, so they vary in all kinds of ways, in sizes and distribution of fat, which makes them a bit difficult when it comes to NIR. So in this case, I used something at that time that I called the big pixel strategy, because now also we wanted to have a calibration that could be used on average spectra, but also on at pixel level. And then we made a calibration that we knew could in a way, as I say, we need to make a calibration that can be used in every pixel. It means that the calibration has to be ready for everything that the pixel can encounter in a way. So we need to record NIR spectra from meat samples that span fat content from 2 to 90%. So here you have these big samples. Each sample is maybe 3 kilos or so of meat. Here you have one with only fatty tissue. Here you have one with very lean meat. I guess this is pork and not beef. And then we made different samples that spanned, so that we got a huge range in fat content. And then we also measure them under different conditions. You can measure them under different temperatures, as you probably know that NIR is sensitive to temperature. But and then we could maybe use. We tested also to measure them at different distances from the scanner in case that affected the signals. And then each sample was measured many times. Like each sample was measured, I think, 6 times. First this surface, and then we turned it around, measured the other surface, and we mixed the sample and so on, and measured them 6 times, and took the average value and matched with the actual fat content that fat protein and water that we measured as reference values. So that means that we made our own samples to calibrate for the images. And so again, in this case, we, as a starting model, we started with 60 samples. They were measured in all kinds of way. Here we have only 4 spectra, typical spectra from these. The red one is from a very fat, the green one is from a lean. And then we had the fat values. So again, we had our calibration set, and we can make a prediction model. So this looks very good, but remember, it's a very long span for all the way from 2% to 80% of fat. So a very high correlation, but the prediction error was maybe around 2.8, so not extremely accurate, 2.8% of fat. And then we could use that model on samples. So here you have a I guess this is beef, and then when that was scanned, we could get a fat estimate of the surface. And you can see here that the lower part here is very fat. Then you have the white part up here, and on the side here, they are also quite fat, but the white side here is not fat. This is connective tissue, and you can see that that part is very lean. And we could also get an average spectrum from the meat and get an estimate of the fat content. And this system, again, it measures to some depth. But of course, these trimmings could be 5 centimeter thicks or 10 centimeter thick. And if we measured only maybe, let's say, 1 centimeter deep, then anyway, it would be an estimate, but not a very good estimate per trimming. For instance, here you could have one trimming here measured on one side, and the same trimming below was just a lot of fat, or a lot of fat. So on one side it would give 13%, on the other side it would give 38%. So and we knew that, but anyway, it is of interest because yeah, here I'll just show this again. If we tested the model on a lot of trimmings, and for instance, you see here on in these red marks here that the same sample here, for instance, measured on one side and the other side gave extremely different estimates, and the same here. But the meat industry, they're not interested in one trimming. They're interested in tons of trimmings, and that means that the prediction error, it decreases with batch size. So this just shows how the prediction error in a batch of meat decreases when so at about 5 kilos you have a quite high prediction error, but then when you average, when the meat comes along the transportation belt, then you average them, and a piece that is very fat on one side and lean on the other side, it will be, let's say, if the fat side is up, you will get a high value, but the next trimming will maybe be with the fat side down. So you'll just average it over time, and that means that it actually works quite well. So at when you measure just 100 kilos, you have low prediction errors, around 1%. And I mean, the industry, they measure 500 kilos in a batch, or a ton per batch. So this actually works, and it is used a lot. So here I just show this is a spectral image of 3 different batches of fat, one that vary in fat content, and you can see the fat on the surface. And you can then also imagine that they, if you scan enough of meat, it will be representative, and you will get a good estimate. So here we don't use a lot of the image in a way, the image information, but we use the imaging capability to capture all as much of the beef or the food as possible, so that we get the best possible estimate. So that's the main important thing here with the imaging. And also, of course, it's when you have an imaging system and you have a conveyor belt, then the samples can come at any position, and that makes it very easy to do imaging. If you do line scanning, then you have to, well, then all the trimmings have to go under a line scan. Okay, so yeah, this is used in the energy, both with people use it and they can in a way use it to adjust the fat content in the batches, or they can also, it's also used automatic sorting based on these measurements, so that they can sort and achieve the batches of a certain fat content. We can also use the visible part of the scanner. So because sometimes it's of interest for the industry to sort out meat with a lot of connective tissue. So the connective tissue, then the meat is of a bit lower quality. So then we can combine a fat image with a visible image showing the whiteness. So if you have an area like here that is white and has a low fat content, then you know it is connective tissue. Or here you have a lot of a white area that is low on fat, then it's a lot of connective tissue. So this is simple classification in a spectral image, so that if they had a lot of connective tissue, they could sort it into another batch that is of, as I said, a slightly less value, but they can use it for other products. Okay, am I talking too long, or is it okay? Okay, you are still there.
It's okay. It's okay.
It's okay. If you want me to, I don't how much. Yeah, okay. I will just talk, and then you just stop me if it's too long. I think I have 2 more examples. This is a crab. In Norway, we produce a lot of crabs. We catch them, we produce them, and we export them to, for instance, Spain and Italy and so on. And the main quality feature here is the amount of meat inside the shell. And it's really difficult to judge if you hold them in your hand. An experienced grader can do it, but it's difficult. And when they process maybe 40 to 60 tons of crab per day, it's impossible to do manual evaluation. So again, it's possible to use this interaction measurement, that you send light through the shell of the crab, and it will interact with the food here in front in the shell, and we will measure the light that comes up again, just as we do with the salmon and the bacalao. And that means that we can measure the amount of protein and fat and water here. So if you have an empty crab with very little food, then you will have mainly water here. But if it's a lot of food, then it will be a lot of fat and protein as well. So here is what we want to do, or what we did. This is a brown crab. It is filled with the liver and the roe here, and as I said, sometimes there is nothing here, especially during wintertime. But a good quality crab, of course, contains a lot of meat, and it's very important for this company to be able to measure this. So we tried this old scanner, and here you can see a spectral image of a crab on one channel. So I worked with this for a while before I, in a way, figured out a good way to do it. So in this case, we work in different stages. First, here are some crabs on the conveyor. They are alive, so sometimes they escape from the belt, but this is from the same scanner as you see, low resolution, but high enough to see what we need. So first we did segmentation. So here we find the entire crab, and then the shell had a different spectral signature than the legs and the claws. So we could find the shell, the brown shell, and then we knew that it was the front part of the shell that is of interest. So then I could just pick out the front part of the shell, and then from that part I could take the average spectrum of the crab. So here you can see there are huge differences between the crabs. So here you have the red one here, contains a lot of fat, where you have Yeah, a quite clear fat peak and so on. And the green one here is mainly water, so it's an empty crab. So it's a very good basis for making a calibration. And you can see here that we have a nice calibration that can actually be used to divide the crabs into 3 groups: empty and medium full and full enough for full. And since the front part of the shell was very, in a way, representative for no meat or a lot of meat, we could also use that calibration, again, a regression vector, in at every pixel. So here you can see images of where we see the fat content through the shell of every single crab. So interesting for the biologists sometimes to see that, oh, some crabs actually have a lot of fat, no, a lot of meat on one side and less on the other, and so on. But mainly this is used for industrial sorting. So that means that what they do is that they sort them in full crabs, and they are boiled and exported to you. And then half full crabs, then they make this product. They open them and they fill the shells, and they sell them, at least here in Norway, as these shells with claw in. And then empty crabs, they just kill, and they take only the claws and sell the claws. So this was one of the first papers we made on hyperspectral imaging, and I was a bit proud at that time because it was on the front page of Applied Spectroscopy. I think the only one with crabs, so that far. So this is a nice application. Here are the number of crabs we measured in about 1 minute. So it was quite quick system, and which is of course important for this factory. And then I think it's my last example. This is a more recent example, just a few years ago. This is from a chicken production facility in Norway. They are measuring every single fillet, and the main problem here is that in the poultry industry they have a lot of problems with different muscle diseases. So here you can see an example of what's called woody breast. It's a muscle disease. It is poor quality. The protein content here is very low, and it's full of water in a way, and the water is very poorly bound to the proteins. So here is normal one, and what I want to do here is to sort them out. So 5 meters down the line here, there is a robot that picks out the bad ones, and they also use the information to try to improve the whole value chain. I will show you this. So here we discovered this just by accident. So I did some measurements for this chicken company, and we just saw that, wow, these wooden breast samples are really strange. And so this relies again on the same spectral region. And the big difference here you see between a normal fillet compared to a woody breast fillet is that we get this very distinct shift in the water peak, and that is due to 2 things. It's due to lower protein in the woody breast, and also due to that the fat is the water is it's a lot of free water inside a woody breast. So that means that based on this, it's possible to actually make images of every fillet, but it's not so important here either to actually image the variation, because the fillets are quite small, and I don't want to cut them either. But so in Norway, the fillets are quite small, but in the US, they are much bigger. So there they are actually using pixel information so that they can cut away parts of the fillet that is very bad, and they can keep the rest for normal processing. So if you see these red ones, they are normal, and the blue ones, they are poor quality. If you see some of them have this small red thing going out, that's that's because this inner fillet is showing up, and that is completely normal. And it's the same here. That's completely normal, but the upper part of the fillet is really poor quality. So that's how this is used. So it is used now in Norway and the US and in Germany, as far as I know. And as I said, in US they are using the pixel information. So there they have a pixel-based model that can grade the different parts of each fillet. So what they can do here is that they can evaluate every flock, and they get the protein value for every bird, and then they can count and figure out how many wooden breasts are there in every flock, and then they use this to discuss and give advice to the farmers. So the farmers who has very poor quality, then this company will visit them and try to change the production so that the production and also welfare of the animals are improving. So I think it's a nice example. And then my last slide here is just to show that I've done something other things than than NIR. This is fluorescence. Some years I worked a lot on lipid oxidation and photooxidation of especially dairy products. So when you expose a cheese or milk, for that sakes, to light, then it gets oxidized. And here's just an example where where the cheese is exposed to light just as it is in the store, and it is packed in like this. And then if you take them out of the package, and then you can make images of the fluorescence, and they will look like this. And these are images that actually show the oxidation. So the purple areas here, they are oxidized. Because yeah, I don't have to go into the reason, but it's riboflavin, for instance, is degraded, and while you see that the bright areas, they are not oxidized because they are protected by the dark packaging material, while the writing in the middle there, where you have white letters, again you see they protect again quite poor against oxidation. So I think it's just a nice example of how you can use spectral imaging to show interesting chemistry. And it's the same here. This is oxidation on a cross section of a chicken burger that has been stored some days in oxygen. And you can see how the upper part and the lower part, where there that has a lot of availability for oxygen, are getting rancid or oxidized. And the reason is that we are measuring fluorescence, and these fluorescent or these oxidation products, they are fluorescent. So if there is a lot of fluorescence, you have a lot of oxidation products. Last slide. This is the last slide. I have a lot of I have colleagues further north in Norway, and they are also working a lot on hyperspectral imaging of fish, and they are using a system from a Norwegian system called Maritech, and that system is in a way very similar to the one from Tomra, but this has a much higher spectral resolution and much higher spatial resolution. They use the camera from Neo high specs, and it is also very quick. So it is optimized to do quick measurements, and I guess you maybe know that camera. So that is a more, let's say, normal hyperspectral camera, where they have been working a lot with illumination to get straight lines. This is also interactance. As you see, there are two stripes here, and two illumination stripes, and they measure the light that comes up in between. Also because they want to measure in depth in the sample, and they are detecting parasites, they are detecting blood spots, melanin spots. They can measure pigment and fat, and it's used more and more in the industry and for different things. So I think that was my last slide. Yeah, thanks.
Thanks, Jens.
Oh, thank you very much. Thank you very much. I think it was really, really nice. And it was certainly a lot of inspiration here for the people We have been commenting some stuff on the example that you have shown. Really, really nice examples. And well, if there are questions, also in the chat. Oh, there might be something in the chat.
There is something in the chat.
Okay, nice. Thank you. Very interesting. We have some applications in tuna and other food products that we can discuss in the future. Okay, yeah. That's the idea as well. That whatever you need to discuss with Jens is here, but not today, or maybe another more specific meeting. I wanted to, well, if there are no questions.
So I hope it was of interest, although I have been working with this particular system, so maybe not that relevant for you, but still much of the, let's say, calibration strategies and so I hope will be of interest. But because you should be able to do the same things with your cameras. I don't know what kind of cameras you use, probably different things.
Well, we have visible, near infrared, and we cover the whole near infrared up to 2,500 nanometers. So it's the same. Well, we collect more wavelengths, but in essence, this is what I wanted to remark from your presentation. It's really nice that you have put a lot of emphasis in the importance of sampling, the importance of the references values that you get there, and one nice thing that you have actually shown in a nice plot is the importance of increasing with batches, with information in your models in order to decrease the error in the future. So I really like this thing. So I wanted to ask you one thing. That's, I mean, how general it can be done, the use of hyperspectral image. I mean, for me, it's more like you can make tailored implementations for solving specific solutions, or can you forecast a kind of global modeling or a global application of, for instance, if you want to quantify fat in not only in fish but also in meat at the same time, how transferable this thing is, according to you?
Okay, that's a very good question. I think that if you're working with hyperspectral imaging in the NIR region, then you have the same limitation as you have, of course, with a single point NIR, and that means that you can try to make calibrations that are as robust as possible and that can be used across different products. But often you will see that if you make, let's say, a fat calibration for trimmings, meat trimmings, and if you apply that on, for instance, ground meat, you will see that you will get good correlations, but you will almost certainly also get some kind of bias. So that you have to at least adjust the calibration so that they work well on your actual sample. But it would be difficult, for instance, to make a fat calibration for meat and apply it on salmon, because they are quite different. So the regression vectors will look quite similar, but you would need to do some kind of calibration transfer anyway. So I think it's difficult to make, let's say, one global model. That's a nice dream, but I think it's very difficult. Actually, last years we have been looking more into Raman spectroscopy. It's not imaging, of course, but it's point measurements also to measure fat and protein, and Raman is less sensitive to sample structure and particle size and these things. So there we see that it's easier to move a calibration from, for instance, intact meat to ground meat. So that's interesting, but with NIR, I think it's difficult.
Mm-hmm. It's really nice that with Raman, I didn't know that. Can you hear me? Yeah. Okay. So I didn't know that with Raman it might be a chance, it might be a possibility. But yeah, I agree with you. And well, we love here cod fish. You are right. We love bacalao. It's
Yes.
one of our. But I wanted to ask you one thing that they will ask me as well afterwards is that when you make your measurements in interactions, that means that you measure the light that penetrates with two light sources. How do you control the amount of or the penetration depth? Is that a way of measuring that?
It's also a good question. I have slides where I can show you, but what you can do, what I have done, because it is important, as you say, it's very nice to know approximately how deep you're measuring. So what I have done sometimes is that you have your system and you can measure in interactance, and then you can take a piece of your sample, maybe 20 millimeter thick. And then you can, if it's, let's say it is a bacalao, then a piece of bacalao, and then in the bacalao you have no fat at all, but you can place it on top of a chunk of, for instance, butter or coconut fat or something, and then you measure on top of the bacalao, and then you do a measurement when it's 2 centimeters, and then you take away a slice and you slice it so that the bacalao sample becomes thinner and thinner and thinner, and then at maybe 1 centimeter you will start to see the fat peak from the butter, because eventually you will get measurements from the butter or from the fat, and then you will see that at 5 millimeter thickness the signal is much stronger, and so on. So I have used that technique to figure out how deep we are measuring, and it works quite well. It's also published. You can actually use MCR then to, in a way, compute or calculate how much signal do you get from the fat at different depths, and so on. So that's one way to do it.
Okay. Yeah. Nice. And the very last question from my side is that will you be so nice to share your slides in PDF with us?
Yes, I can do that. So
Okay,
as I
perfect.
said, most of this is already published, so you can find the papers about this. So it's okay, I can share them.
Okay. So there are more questions? No? Okay, so Jens, thank you very much.
Thank you.
It's a pleasure. I hope it was useful.
Really nice.
Okay.
No, it was really useful.
Oh, by the way, I have my bacalao shirt on today. So I got it in Portugal this summer.
Okay, so next one in Basque Country is much better. Trust me.
The one in the Basque Country, I know.
Yeah, it's much
I know.
better. So next one.
Yeah. My favorite bacalao recipe is from the Basque Country. So, okay. Yeah.
Okay. Thank you very much.
Okay. Bye. Thanks.
Bye.
Bye.